The next thing we'll look at is the idea of direction fields. And for these, we're going to consider these first order equations, dy dx equal to f of x, y. So the left-hand side should just be the derivative, and the right-hand side can have any combinations of x's and y's. Since we know that the derivative is just the slope, this gives the slope of our solutions at each point. So it does tell us what the slope of each point is, which can be very helpful in our direction fields. So let's look at an example first. Let's consider the differential equation derivative of y is equal to x squared minus y, and we want the solution to pass through the point -2, 1. Well, we can actually stick in -2 for x and 1 for y. And when we do, we get that the derivative has to be equal to 3. So the solution has to have a slope of 3 at this particular point. Let's consider the same differential equation, but this time the point -1, 1. This time, when I stick in -1 for x and 1 for y, I get that the derivative is equal to 0. So a solution passing through the point -1, 1 has to have a slope of 0 at that point. So now that we have that, what exactly is a direction field? The idea of a direction field is we find out what the slope needs to be at a lot of different points, and we draw these little short segments at those points to kind of give us what the slope should be at that point. And the idea is to help us draw any particular solution. So let's look at an example. Here's the example we were considering earlier, the derivative of x squared minus y. The derivative is equal to x squared minus y. We said at the point -2, 1, it had to have a slope of 3. So if I look at the point -2, 1, we should see approximately a little segment of slope 3. I also said at -1, 1, it had to have slope 0, and so you can see at that point we have something with slope 0. And this is the idea of a direction field. And like I said, it can help us draw solutions. So here's the exact same direction field, but this time with some solution curves drawn in. And we can see that the solution curves do follow the general pattern of these lines. Let's look at a couple of more examples. This time I'm looking at the derivative of y equal to -2y, and here's my direction field for that one. Once again, we can look at putting solutions in here. So here's that same direction field with several solutions drawn in. We can see that any point, if y is equal to 0, the slope is going to be 0, which is this horizontal line on the x-axis. So at any point that if we pass through any point 1, 0, 5, 0, -20, 0, it would correspond to this one since the slope at all of those points would be 0. Here's the direction field of the derivative of y equal to -y over x. And once again, here it is with some solutions drawn in. So we can see once again that if y is equal to 0, this is going to correspond to a horizontal line. In addition, if x is equal to 0, it'll correspond to a vertical line, since then the slope would be undefined. And other than that, we can kind of see these hyperbolas that would give me my solutions. So let's look at how we might actually want to use one of these. Here is a differential equation, dp dt equal to p times 2 minus p. And this is the logistic equation for the population p, given in thousands, at time t for a certain species. So we want to ask some questions about this. The first question, we have an initial population of 3,000. So that means at p of 0 is equal to 3. So at time 0, we're at 0.3. What can we say about the limit as t goes to infinity? Well, we can see as we follow these general curves, we're going to be stopping at this line. It's going to get closer and closer. So essentially, we can say that the population is approaching 2,000. So if our initial population starts at 3,000, it's going to decrease to approach 2,000. And we should notice that this is going to be generally true for all of these. No matter where we tend to start, this 2,000 is going to be our limit. Whether we start above, if we start below, it will also curve in. If we start above, it will curve down. So if we start with a population below 2,000, we will increase up to 2,000, but we'll never cross that threshold. If we start with a population above 2,000, we'll go down to 2,000, but once again, we'll never cross that threshold.